When we talk about psycholinguistics, what do we mean? Psycholinguistics is a field that combines psychology and linguistics to gain a deeper understanding of human language. We can also say is the relationship or interrelation between linguistic factors and psychological aspects. What do we mean by linguistic factors? These are an example, a good example is phonetics that has to do with sound pattern in a language. And also the psychological aspects, that's where the emotions comes in, fear, happiness, anxiety, and all of that. So we'll be covering, I think this last, we would have covered the following topics. That's the one factor and over, that the assumptions, how do we compute, and then the interpretation. Then we also apply this to a real life example and then visualize our mobile result. So what do we mean by ANOVA? In statistics, when we talk about analysis of variance, is a you can recall in the last class when we discussed t-test, we said we use t-test for comparing means across two groups, if you can recall. But in this case, ANOVA is also a parametric test to compare means, but in this case, we are dealing with more than two groups. So ANOVA is a statistical method used to compare means across three or more groups, unlike the t-test, whereby we deal with just two groups. It determines whether the differences between groups are statistically significant. Yeah. Can you still see my notes? Hello? Are you all see my screen?
Yes, I can.
All right, thank you. So in linguistic or in psycholinguistic, what do we use ANOVA for? We use it to realize variables such as the reaction times, speech error, memory recall. An example in psycholinguistics is a perfect example is if you want to see what type, like noun, verb, adjective, pronoun, reaction time in a lexical decision task. Now, when do we use ANOVA? Like I mentioned earlier, a t-test is used to compare two means, while ANOVA is used when comparing three or more groups to avoid the increase of type 1 error caused by multiple t-tests. What do we mean by type 1 error? For instance, when we say that we reject the null hypothesis when it is actually true, when we are not supposed to reject it, then that's what we call the type 1 error. We have committed an error which is type 1. Why will you reject the null hypothesis when it is actually true? Now, a good example of t-test is like we discussed in the last class. Another good example is comparing reaction times between monolingual and bilingual speakers. That's just two groups. Reaction times between monolingual and bilingual speakers. The two groups here are the monolingual speakers and the bilingual speakers. But when it comes to ANOVA, we are using more than two groups. ANOVA compares interactions between more than two groups. That's where we are comparing the reaction times across monolinguals, early bilinguals, and then late bilinguals. In this case, we have three groups. Now, what are the assumptions that should be followed when we are dealing with one factor and over? Just like when we mentioned in the last class that yeah, running a t-test, then a set of assumptions must be considered. ANOVA also assume that the observations must be independent. That is, each participant tested separately or each group tested separately. Then the data should also follow a normal distribution within each groups. Also, homoscedasticity, that's the equality of variance. The variance of each group should be similar. What if these assumptions are violated? Then that's where the non-parametric test comes in. So just give me a minute. Okay, so that's when the non-parametric test comes in, such as Kuskawalis. The Kuskawalis is an example of a non-parametric. Like I mentioned in the last class, we said we have parametric test and we have non-parametric test. A good example of a non-parametric test is Kuskawalis, Mans, Whitney. We mentioned that in the last class as well. So, but we only use that when the assumptions above are violated. Also, we can apply data transformation. Good example is the log transformation. Now, how do we compute a one-factor ANOVA? So in how do I call it? In ANOVA, ANOVA works by partitioning the total variance in a data set into two sources. And these sources are the variance between groups. We also call them treatment effect in statistics. And the variance within groups, those are the errors. We call them errors in statistics. Now, the F in this case is the F statistics that's being used to measure the um, analysis of variance. F statistics has to do with analysis of variance to determine if a group means are larger or are different, wider or not. So the between group variance different, there are differences due to the experimental conditions why they within groups, also known as the errors. There are random variation within each groups. Now, a higher F value is important to note this. A higher F value or a low P value, it tells us whether at least one group mean is different or not. Now let's look at this in let's try to apply this to a real life situation. A good example we have here is the reaction time in a lexical decision. So the research question here is that does what type affect reaction time in a lexical decision task? Is good to set an hypothesis even if it's not written down. We all know that the null hypothesis tells us that no significant
Hello, everyone.
Hello, sir.
Yes, sir.
Yes, sir.
We are
Yeah.
Hello,
Let's
sir.
let's wait for her to rejoin. Okay.
All
Okay,
right, sir.
sir.
All right, sir.
Okay, so sorry about the loss in connection. Please, where did I stop? Where was the last thing we got I mentioned? I'll try to share my screen again. Hello? Hello, can anybody hear me now?
Yeah, we are with
Yes.
you.
So where was the last page that was before my connection broke up?
We were on application. I think application reaction time in lexical decision.
Okay, okay, thank you. All right, so we are trying to apply this to a real life situation now. And a good example we have here is to see if what type affects reaction time in a lexical decision task. And our hypothesis is as follows to say, the null hypothesis, we usually say there's no significant differences. In this case now, there's no significant differences in reaction times across word types, while the alternative says at least one word type has a significantly different reactions. And the data we collected is the word type. We have three different word types. You can call them the groups: the high frequency, the low frequency, and the non-word, and their reaction times. Now let's test if the reaction times differ across the three word types. So here we now go to our software to input our codes and perform this analysis of it. So if you have it your, how many of us have it our laptops and you can follow me with these codes? Is anybody running this with me on the laptop? Hello? Okay, nobody is joining with the laptop. All right, so I'll go ahead and open my house software now. And then we run our ANOVA to see what we have. Can you all see my R screen now?
Yeah. I can see. Everyone, I can see.
All right, so I've already copied my quotes. The code is in the same note as on our Google Classroom. So I copied the codes already into the house software. I'll just run it from there. But first, the first step in performing a one factor ANOVA is by loading your data set first. In this case, we try to create our data set as listed above. The lexical data is what we are naming our data. Now we create a data frame. Data frame is used to create a data set in R. You are trying to create your data set manually. That's if you are not bringing it from Excel. So we have 9 participants. That's why we have 1 to 9 here. Then the word type, we have the high frequency, the low frequency, and then the non-words, and also the reaction time. So when you copy this into your R screen, your source pin. So this is the first code. I'm trying to create my data set. Let's run this and see what we have. So I've already run this by creating my lexical data set. Now the next code is saying, sorry about this. So after creating my data set, let me now view the data and see what we have. So this is our data set. We have 9 participants, 3 different word types, and then the reaction time. Now the next thing to do is to perform our ANOVA. Now the code to run in one factor ANOVA. In R, we have different functions. And the function for a one factor ANOVA or ANOVA, as the case may be, is AOV. What do we have inside the AOV? That's the reaction time. We are using the reaction time as the leading factor here because we are trying to see if to test if the reaction times differs across the three groups that we have. That's the three word types. Now the reaction time to that word type, those are the word type consists of the three different groups of word types that we are using. Now the data we are trying to consider here is the lexical data. Now let's run this in now and see what we have. So we've already run the ANOVA, but we need to view the results by using the summary function, because here we said ANOVA results should be all of this. Now let's view the summary of ANOVA results, and here's what we have. Now this is our result. Can please confirm that you can still see my screen? You can see my result on the screen.
Yes, ma, we can.
All right, thank you. So in this summary, we have different, you can see we have different values and all of that. But what are we interested in specifically? Interpreting, that's when interpreting the ANOVA results comes in. But before then, we should know that the F value, as mentioned above, mentioned this above, the F value measures the variance between the groups versus within the groups. Meanwhile, the p-value helps us to determine whether to reject or fail to reject the null hypothesis. Now let's interpret our ANOVA result. In this case, what's our F value? This is our F. The column for F value, we have 76.63, whereby our p value, which is this, is 0.0000535, like that. So because of that's how I write it there. Exponential minus there means the 0.000. So this is way less than 0.05, which is our alpha value or significant value. So the from our interpretation, from the interpretation guideline here, a larger F means greater differences between the groups. So if we look at this, can we say if our F value is large or not? Can we tell? Who can tell us if the F value is large or not?
I think the F value is large because maybe it's 76 over 100 or something like that.
But you are not sure what the maximum value should be or the minimum value.
Yes, ma'am. I'm not really sure about the maximum value.
Okay, so you are right actually. Oh, you are right actually. Sorry, who just spoke now? Is it Kolawole or
Yes, ma'am. Color.
okay, Kolawole? Thank you. So you are right, but in statistics, if our F value is large, like we mentioned, it suggests that the means are larger or the difference are greater. So if they are close to one, it means that the different groups variance is similar to the within group variance. But in this case, the F value is not close to one, is way larger than one. So we can say the F value is larger. This means that there is the greater differences exist between the group means. So in this case, our p value is less than 0.05, tells us that we reject the null hypothesis. Let's confirm this value. These are p value and these are F value. Our F value is large. This means there is a greater difference between the means. And our p value is less than 0.05, then we reject the null hypothesis. Now, the next step is to say that if the ANOVA is significant, can we say our ANOVA is significant or not? Anyone? Who can tell us if our ANOVA is significant or not?
I believe it's significant.
Cassava, is that
Yeah,
it?
it is. It is significant
Okay,
now.
okay, so why is it significant?
Okay, Cassava will answer that one before me. Thank you.
Okay, you are handing over to Cassava now. Who is talking? Is it Cassava or Didion.
I
Who wants
believe
to answer the
I believe
question?
it's significant. I believe it's
Okay.
significant because it helps us to determine our p-value, in which case we are able to reject our H naught, which shows the significant effect of what type of reaction type.
Okay, thank you very much, Cassava. Yeah, Cassava. Cassava, right? Okay, that was a brilliant one. So our
Yes, yes.
Hanover is significant because we already said our null hypothesis is that there is no significant difference. And in this case, our p-value is less than 0.05. We are rejecting the null hypothesis. Otherwise, we fail to reject. Now, in this case, that we are rejecting the null hypothesis, we are going for the alternative hypothesis, which says what? There's significant difference between the mixed group. So that's why we say our Hanover is significant. Now, after running the Hanover and finding that there's significant difference between the word types, at least we know that one word type is differs from another. However, our Hanover does not tell us which word type differs specifically or how are they differ. So that's why a post hoc test we use will help us to determine which groups have significant differences and then compare the results to see where the differences lies. So a common post hoc test that is used in analysis of variance is the Turkey HSD. Now to run a Turkey HSD in R, that's where the Turkey HSD function comes in. So let's run this and see what we have in our R. So we have this whereby we have the Turkey multiple comparisons of means. So these are our main results whereby we see the word type. We have three different word types. That's the low frequency, the high frequency, and the non-words. So these are the differences. We have the lower value for the confidence interval, the upper value, and then the p-values for each of these groups. Now, the first one here is telling us that the low frequencies versus the high frequencies, their difference is 66 points. This, whereby the non-words versus the high frequency, this is the difference, and then the non-words versus the low frequency, we have 80. Now, amongst these three, we observe very well, we can see that the highest difference in this case is the non-words versus the high frequency. Now, what does this tell us? This simply means that the high frequency words have the highest time to, the non-words have the highest reaction time against the high frequency. How best do I interpret this for you to understand? Okay, the interpretation is there. So from here, we are trying to say that the highest difference here is the 146.67, whereby this is equivalent to the non-words versus the high frequency. And this tells us that the highest difference lies in this non-words versus the high frequency. What does this mean? Is that the let's go back to our hypothesis. Our hypothesis tells us that at least one word type has a higher significantly different reaction time. But since we reject the null hypothesis already, in this case, the non-word type has a higher significantly different reaction time. In fact, it has the highest, that's the non-word type against the high frequency. It has the highest significantly reaction time because it has the highest difference in this case, and that's where the difference lies. The second higher here is the non-word, which has a low frequency. The non-word versus the low frequency, followed by the low frequency versus the higher frequency. Now let's go back to the. So in summary, this Turkey HSD helps us identify where the differences lies. That's the high frequencies versus non-what as shown in the results. Now, the next thing, we might be interested in visualizing our results to see if the means are clearly different, if there are overlapping distributions, or there's a pattern of reaction time. So the box plots will help us to do this clearly. Let's run this code and see what we have here. So here's our box plot. And what does this tell us? That the higher frequency watts have the lowest reaction time. This is the higher frequency watts. And the reaction time is the lowest, followed by the low frequency watts. And then the non-watts have the highest. They take the longest to react. And that's what the box plot here tells us. So in summary, we use the ANOVA to compare means across the three different watt types. And one factor ANOVA requires normality, that's the absorption, like we mentioned, the independence, normality, and then the equality of variance. Also, if the ANOVA is significant, then the post hoc test, in this case, we use the Turkey HSD, we determine which group exactly differs. And then the reaction time data in psycholinguistics is commonly analyzed using ANOVA. So, and with this, we have come to the end of the class. So if there's any other question, we can take that now, or we hand over to Dr. Peter to round up for us. Do we have any question? Okay, DJ, please go ahead. Your hand is up.
Yeah, thank you, ma. All right.
You're welcome, sir.
I have a few questions. I did not really get what's the full meaning of that F value. That's the first question. So, what F value stands for? And
Okay.
also, I also want to know when we say we are uploading our data, what if we have our data saved already, maybe as a CSV file or any formats in our system? What would be the syntax of uploading the file directly to our workspace?
Sorry,
Because
can you take the second question again?
like we have our data already, maybe in a spreadsheet that is Excel format or CSV format that's already saved on our system. So how do we, is there any syntax that we can, you can just run as a command and you upload it to our CSV, to our workspace directly? I don't know if you get my question.
Is there any
Then
way we
my
can bring in our data to the house space, right?
using code, that is using
Okay, I
using
get that.
code.
Okay.
Then my last question is that all this while we've not personally, this is my personal concern, I've not really seen your face since we started. Actually, we know almost all of our lecturers. If you see them on the way, you greet them, good morning, ma, good morning, sir. But unfortunately, we've not seen your face since the first day. I don't know if next time you could just present with your face, because that's a way of impacting to our life. Thank you. Those are my concerns.